Hello, I'm going to do a combination for Unit 3, 4, and 5 for Chapter 8, trying to put in all of them together as one piece and then going on reviewing each section by itself. In order to do that, I'm going to share my PowerPoint with you. And then I'm going to start describing it. We're going to combine in this particular short PowerPoint, I'm going to combine Unit 2, 3, and 4, interpret for each structure, draw the Lewis dot structure using the rules, then assign molecular geometry based on VSPER theory and electron pair theory, name the geometry based on both molecular and electron pair geometry, calculate how to calculate formal charge on each atom, determination of the bound angles because of repulsion, you can find out, then bond polarity, molecular polarity and bond order, nature of the bond by using the electronegativity charge, and then how to designate and define incomplete octet, expanded octet, odd electron, and resonance structures. Before we go to any other items, it is very important to check what type of bond we have and what are the definitions associated with it. Because throughout this particular PowerPoint presentation, I am just going to use the definitions so that you can understand why we do it in this way, so that a repeated use of terminology will have a good impact on memory and retention. A single covalent bond represents a pair of electrons shared between two atoms. The atoms can be same or different, but when the atom is the same, then the pair is equal, the electronegativity is zero, because we can subtract electronegativity of same atoms is similar. So on subtraction, it gives us zero. And therefore, there is no distortion of the electronic field. And the pair of electrons between the two atoms can be indicated by a line. Next is the double covalent bond. An example of the double covalent bond is the sharing of two pairs of electrons or 4 electrons between two atoms. And the example for such a type of molecule is the oxygen atom. Again, you can see the structure. This oxygen belongs to group 6. 6 times 2 is 8 electrons. So the oxygen molecule has 12 electrons, making, if you divide it by 2, then you get 6 pairs. And 6 pairs of electrons have to be uniformly distributed between the two atoms. And so we can see that there are 2 atoms on the top, 2 lone pair electrons on each oxygen atom, and a double bond. A single double bond is between the two atoms, accounting for each 6 electron pairs. Now, if you close a shadow or shade one of the oxygen atoms, you will see that the other atom has 8 electrons. And in the same way, we find that if you close the other oxygen, the other atom will have 8 electrons. And so in this case, the oxygen atoms complete their octet. Now, electrons that are not used in bond formation are called as lone pair electrons. So in an oxygen molecule, you do not have any single covalent bond. You have 1 double covalent bond and 4 lone pair electrons. Now, the triple covalent bond consists of 3 pairs of electrons shared between between two atoms. And an example of a triple bond is the nitrogen molecule, where you can see in the figure that you have 3 pairs of electrons between the 2 nitrogen atoms, making 6 electrons, and the remaining 2 electrons are assigned to the 2 atoms and equally distributed, and therefore we find that each nitrogen atom completes its octet and you get a triple bond. So here, there is nitrogen molecule does not have a single bond, but it has one triple bond and two lone pair electrons, each lone pair assigned to one nitrogen atom. Now, in order to check for bond polarity, since all of these are of the same elements, then these molecules will have no polarity and they are non-polar molecules that are there. Now, if you have to check bond polarity, then you have to check the electronegativity chart, and then the delta change in the electronegativity is obtained by using the electronegativity of the NRN and subtracting the cation electronegativity. The difference gives you the difference in electronegativity, which can be used to designate what type of bond it is. If the value lies between 1.7 and 3.3, then the bond is ionic. Between 1.7 and 0.5 and 1.7, then the bond is polar covalent, and between 0.1 and 0.5, then the bond is non-polar covalent bond. So it's just a question of just subtracting and find out. Always check the molecule for symmetry, because a bond, now you have to also be able to differentiate between a bond polarity and a molecule polarity. So in order to differentiate between the two, the bond itself can be polar, but if the molecule is symmetric, then the molecule will not be polar, because there will be a uniform distribution of charge, and that is based on symmetry of the structure that is there. Next, we come to formal charge. The calculation for formal charge is group number from which the element is, take away the number of lone pair electrons assigned to a single atom plus 1/2 the bonding electrons. This is because each element brings its own electron for sharing to form a bond, but the lone pair is not used up and it belongs to the atom itself, and therefore you can find out the formal charge. The formal charge is generally assigned to molecules, and it is different from atoms in a molecule and is different from the oxidation number. Oxidation number is the charge an atom acquires in order to make the molecule neutral, whereas the formal charge is the charge on each atom assigned based on the distribution of electrons and bonding electrons and lone pair electrons. And generally these charges are assigned. Like if there is a bond that is highly electronegative, then it is assigned the greater negative charge. And also the formal charge are of low values as compared to the oxidation number charges. Then we know that next we know that bond order. Bond order is the number of bonds, electron pairs designated between similar atoms. So you cannot change the atoms. So you count the number of electron pairs distributed between the atoms and then determine also the type of bond that is there. And so in that case, the ratio of the number of electron pairs divided by the types of bonds that are present will give you the bond order. And remember, bond order can be 0 as well as negative, as well as fractional charges. That is because of resonance and unequal sharing of the presence of electrons that is there. Molecular and geometry and electron pair geometry are based on the VSPER theory. VSPER theory stands for valence shell electron pair repulsion theory. So the electron pair is shared between the atoms, as we have seen. So it is basically an electron pair repulsion theory, where electron pairs, as we know, repel each other. Because of this repulsion, they get a geometry around the central atom. The central atom is generally the most electropositive element in the formula of the compound. And so you get two types of geometry. One is the molecular geometry, which indicates the manner in which the atoms are bound to the electrons, a central atom, and the electron pair geometry indicates the number of electron pairs that are bounded to the central atom. Now, how do we calculate the write the Lewis structure? So once we have, how do we calculate the Lewis structure? In order to calculate the Lewis structure, first of all, look at what type of ions are there. An ion will add an electron for each negative charge. For a cation, you have to subtract the number of electrons lost. Then you draw the skeletal structure with the least electronegative atom occupying the central position. Hydrogen and fluorine always occupy the terminal positions. Hydrogen cannot take more than 2 electrons, and fluorine can accommodate a maximum of 8 electrons or 4 pairs. Place 1 pair of electrons between the bonded atoms. Complete the octets of the atoms attached to the central atom by adding electron pairs. Count the total number of electrons, subtract from subtract. Step 1, place all remaining electrons on the central atom in pairs. If the central atom has fewer than electrons than an octet, see whether you can form double or triple bonds as necessary to complete the octet. In some cases, it is not possible to form the octet because the sharing of electron does not occur. In that case, you find that you have a molecule that has an incomplete central atom, incomplete octet. Hydrogen will never have lone pairs, or will it form multiple bonds. Now, using the Lewis dot structure and the octet rule, the electron pair between 2 atoms of hydrogen in a hydrogen molecule is represented by dots. So each hydrogen atom brings 1 electron. It is placed equally in between, shared equally by the 2 hydrogen atoms. And because it is shared equally, we have a single hydrogen bond. And there is no distortion in the bond, and so we call this a single covalent bond. Next, in order to see how, now we're going to slowly combine each and every one of the concepts that I introduced at the beginning. First, let's look at the molecule hydrogen fluoride. Hydrogen belongs to group 1, therefore it brings 1 electron. Fluorine belongs to group 7, so it brings in 7 electrons. So the total number of electrons present, so the total number of electrons is equal to 7 plus 1 divided by 2 equals 4 pairs have to be distributed. So now we know that hydrogen can only take 1 more electron because it's outside. And so hydrogen brings in its pair a single electron, and you get a bonding one bonding electron between HF, that is shared between H and F. The remaining 6 electrons or 3 pairs of electrons are assigned to the fluorine atom. And therefore, we have a single bond. In HF, you will find there is a single bond and 3 lone pair electrons, which are not used in bonding. Now, the question is HF bond polar? So we see that fluorine is the most electronegative element. And so it will have a tendency to distort and pull the electron towards itself. The electronegativity of hydrogen is 2.2. So change in En is equal to 4.00, take away 2.2 is equal to 1.8. And therefore, the bond is polar because it is greater than 1.7. And so it is a partial, it is an ionic bond. And so we know the bond is polar. That means hydrogen, once fluorine pulls the electron towards itself, then hydrogen will acquire a small positive charge and fluorine will acquire a small negative charge. The molecule itself will be neutral. And so for that, you have to remember. Now, next, let us look at the bond angle. This is a straight line. As you can see, between HF, there is a single line. The bond angle is 180 degrees, and therefore the molecule has a linear geometry. Linear, it is in the same plane. So the bond, there is so far, we see that the bond is polar, a single covalent bond, 3 lone pairs, and we have the molecule is polar with a slight positive and negative charge. Next, we come to how do we get the bond, how do we get the formal charge? The formal charge is calculated as group number. Group number, take away the lone pair electron, lone pair electrons, plus 1/2 the bonding electrons. If we do this, then for hydrogen, it belongs to, so formal charge for hydrogen, formal charge for H is 1. There is no lone pair, so there is no lone pair electron, plus 1/2 times 2, which is equal to 1. So now we see 1 take away 1 equals 0. So, and 1 take away 1 is 0. In the case of fluorine, just give me a minute to rearrange that. In the case of fluorine, what you will see is, let's look at it for fluorine that we have, so that for fluorine belongs to group, fluorine belongs to group 7. Take away, there are 6 electrons for lone pair, plus 1/2 times 2 electrons, which gives us 7, take away 7, which is equal to 0. And so, which is equal to 0. And therefore, both the formal charge on hydrogen is 0, and the formal charge on Fluorine is also 0, and this is how you calculate your formal charge. Now, bond order, there is only one type of bond between H and F, so bond order is 1. So one type of bond, one type of electron pair, and so we have bond order equals 1. And with this, we have done almost everything. The geometry is linear. The angle is 180 degrees. And this is how we do all the calculations that are there. So bond is polar. Six lone pair electrons, one single bond. The single bond is polar. Formal charge 0 on hydrogen, 0 on F, so it is a stable molecule. And this is the chart for which you can use in order to understand how to calculate the bond polarity that is there. Now, let us look at the structure, Lewis dot structure for NH3. The rules are that you must place the atoms symmetrically, distribute that. First, you form the bonds between the atoms at the central atom, and then distribute the remaining electron pairs in such a way that you do not assign hydrogen any more than one pair of electrons, that is 2 electrons. So now, how do we calculate it? We see that nitrogen belongs to group 5. So here we can write that nitrogen N brings in 5 electrons plus 3 times 1 electron, which gives us 8 electrons divided by 2, makes it 4 pairs. This is how the pairs of electrons are calculated. Now, compared to hydrogen, nitrogen has a lower electronegativity. You can see nitrogen, nitrogen is the central atom because hydrogen, even though nitrogen has a higher electronegativity, hydrogen cannot form the central atom. And so we see, and you can see how the same thing what I did in calculation is shown below, how we got 8 electrons on 4 pairs. Form the single bond between the nitrogen and hydrogen. So from the 4 pairs that we counted, 3 pairs have been used by nitrogen. Nitrogen-hydrogen bonds, leaving us 1 pair. Now, since the duplet for hydrogen has been completed, the lone pair electrons must go on top of nitrogen, and therefore you have your structure for nitrogen that is there. And so now we will see first, the bond order is 1 because there is only 1 bond. The formal charge is, for all the hydrogen, the formal charge is the same. Group number is 1. There is no lone pair on hydrogen. And so 1/2 the bonding electron. So 1/2 of 2 is 1. 1 take away 1 is 0. Then let's come to nitrogen. Nitrogen is group 5. It has 2 electrons from the lone pair, and it has 6 pairs. 6 electrons are used in bonding. Half of 6 is 3. 3 plus 2 is 5. 5 take away 5 is 0. So both nitrogen and hydrogen have a formal charge of 0. So now in the molecule NH3, we find 3 single bonds and a lone pair of electrons that are there. Then, is the molecule polar? The NH bond is polar because And electronegativity for nitrogen is 3. Electronegativity for hydrogen is 2.2. So 3 take away 2.2 is 0.8. So the NH bond is polar. However, by looking at the structure, you see that 2 of the NH bonds cancel each other. And the nitrogen has a lone pair electron, and therefore the molecule, if a molecule has a lone pair electron on it, that molecule is polar. And so you will find that the nitrogen, ammonia, NH3 is a polar molecule in which the electron, the direction of the polar bond will be from hydrogen to nitrogen to the lone pair electron. So that it's how it will be pulling out. Then for the VSPER theory, generally speaking, we will find this as trigonal pyramidal. And how we get that is because there are 4 bonds on the central atom, with the lone pair that is sitting on the top needs a larger space than a bond, and therefore it will tend to push the hydrogen bonds inward, giving it a geometric angle of 107.5 minutes. And as soon as the bond angle, so in this structure, as shown, the bond angles are 90 degrees, but actual measurement shows it to be 107.5. Bond angles greater than 107 generally tend to have a geometric shape. And so this is called as the trigonal pyramidal structure. So the electron pair geometry is tetrahedral. The molecular geometry is trigonal pyramidal. Now we come to carbon dioxide. Again, we get carbon is the central atom, more electropositive than oxygen. The valence electrons are 4 from carbon, 6 from oxygen, giving you 16 electrons, because 6 times 2 is 12, 12 plus 4 is 16, 16 divided by 2 is 8 pairs of electrons have to be distributed. So the single pair, from the 8 electrons, if you take out 2 pairs, you are left with 6 pairs of electrons. The atoms on the extremity are 2, so 6 divided by 2 is 3 electron pairs per atom, or per oxygen atom. As soon as you give that 6 electrons per oxygen atom, you find that the oxygen atom has completed its octet. However, carbon has not completed its octet, and therefore 1 lone pair electron from both oxygen atoms come in between to form a double bond. And you will find that now carbon completes its octet, oxygen completes its octet on both sides. So the bond is linear, again 180 degrees. First. Next, is the bond polar? The answer is the bond, CO bond is polar, but the molecule is not polar, non-polar, because the polarity extends onto opposite sides and cancel the effect. Next, the formal charge. Formal charge for each oxygen atom is the same. You have oxygen belongs to group 6, take away 4 electrons, plus half of 4 electrons from bonding electrons. That is 4 plus 2 will be 6. 6 take away 6 is 0. On carbon, if carbon belongs to group 4, no lone pair electrons. So half of 8 electrons is 4. And so 4 take away 4 is 0. The bond order is 2 because there is only 2 types. 2 double bonds, and there is divided by 2. 1 type of bond, and there are 2 double bonds. And so you have the bond order 2. And the bond angle over here, because the structure is linear, is 180. Now we look at formaldehyde. Now here I'm going to just discuss how. First, you have carbon brings in 4, hydrogen brings in 2. Why 2? Because there are 2 hydrogen atoms. 2 times 1 is 2, plus oxygen 6, gives you 6 plus 4, 10, plus 2 electrons, 12 electrons, making it 6 pairs of electrons to be distributed. So join the atoms. So carbon is the central atom, more electropositive. Then you have a carbon, hydrogen on opposite sides to maintain symmetry. And then you have the oxygen atom. Now, when you distribute these electrons, pairs, you find 3 pairs have been used up. And so there are 3 pairs left and they go onto the oxygen atom. But when you assign it to the oxygen atom, then what happens is oxygen completes its octet, hydrogen completes its duplet, but carbon does not complete its octet. Therefore, one of the pairs goes in between and forms a double bond between carbon and oxygen, as a result of which all the atoms complete their duplet or octet. Now what you see is this, that 2 other possible structures are there. One is HOH. Oxygen as the central atom and carbon is attached to the oxygen. Now both the structures shown are not possible and hence we cannot admit. Now how to calculate the bond order? In between carbon and oxygen, the bond order is 2. Between carbon and hydrogen, the bond order is 1. The structure has 1 double bond, 2 single bonds, 2 lone pair electrons. The bond is polar because of oxygen being more electronegative than carbon. And so it is a polar bond that is there. And the carbon-hydrogen bond, even though polar, the polarity is cancelled because they are on opposite sides. The VSPER geometry, when it do it, the carbon atom generally tends to have a tetrahedral structure. And therefore, because we have 6 pairs of electrons to be distributed, it gets a triangular trigonal planar shape. And therefore, the overall polarity will be neutralized. And so you have a symmetric structure over there. And you can see the common patterns of bonding in the Lewis structures in the chart below. And this chart is also available in the actual documents that are there and how to draw it. So now isoelectronic species, you need to know there are species which have the same number of electrons. And so it can be a cation, it can be a neutral molecule. And you can see the geometry over here. In the case of nitrogen molecule, carbon monoxide molecule, the geometry is linear, 180 degrees. And the formal charge, now you've learned how to calculate it. Both will have 0, 0. Same thing for carbon. You will have carbon as +1, 3, +2, 5. And carbon group number is +4. So +4 minus 5 is -1. And in the case of oxygen, group number 6, and you have 3 electrons coming in from the bond +2. So 6 take away 5 is +1. So here there is a slight change, but this is how the molecule exists, and so we cannot change its polarity over there. Now, the Lewis dot structures tells us how atoms are connected in a molecule. Bonds, pairs are BP, lone pairs are electron pairs, and the 3D shape of a molecule is, however, determined by the bond angles that are present. And therefore, experimentally, the CHC bond are found to be 109.5 degrees. If this is the case, the molecule cannot be planar as indicated, because 90 times 4 is 360, whereas 109.5 times 4 is 438. Therefore, the molecule, methane molecule CH4, must be a 3D structure since the sum of the angles is greater than 360. And in order to accommodate this higher molecule, the shape becomes a tetrahedral shape in which one carbon bond comes towards us, the other one goes inside, and the remaining two are same on the same plane. And therefore, the bond angle is indicated as shown. Symmetry is maintained, and so it is nonpolar. Again, you can calculate the formal charge. In order to predict the molecular shape, we assume the valence electrons of each atom in the molecule repel each other. When this occurs, the molecule adopts a 3D geometry that minimizes the repulsion, where lone pair repulsion is greater than lone pair bond pair repulsion is greater than bond pair repulsion. This process is known as the valence shell electron pair repulsion theory. Two shapes arise from using the valence shell electron pair repulsion. A molecule can be described in terms of the distribution of the bonding atoms around the central atom, which is called as the molecular geometry. And a molecule can also be described in terms of the bonding pair of electrons and lone pair electrons about the central atom. The lone pair distribution or the bonding distribution of electrons is called as electron domains. And here are the electron pair geometries of various atoms surrounded only by single bond pairs. And the general formula that we generally use is AX. AX is linear, AX2 is linear, AX3 is trigonal trigonal planar. Then if you have AX4, that means 4 bonding electrons. X is the atom at the extremity. A is the central atom, then the angle is 109.5. If you have 5AX5, then you have 5 electron pairs. 2 pairs are distributed along the axial and 3 along the axial plane, 3 along the axial plane, 2 along the equatorial planes, and AX6. You have 6 pairs of electrons, and the general geometries are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And for each of these molecules, we can find out the formal charge, the bond order, bond polarity, molecular polarity. And if you want to better understand, you can see the balloon models. Linear is 2. Trigonal planar is 3, tetrahedral is 4, trigonal pyramidal is 5, and octahedral is 6. And the different other shapes are shown over here. And you can see, depending upon the number of lone pair electrons, the electron pair geometry remains the same. But the molecular geometry changes depending upon the number of atoms attached to the central atom. If all 5 atoms are attached to the central atom, you get trigonal bipyramidal. If 4 atoms are attached, then we get seesaw. If 3 atoms are attached, then you get T-shape. And if 2 atoms are attached, then you get linear or an AX5 bonding system, that is 5 pairs of electrons. On the other hand, if you have 6 electron pairs attached to the central atom or distributed around the single atom, then you have, when all the 6 atoms are complete, then you have octahedral. When 5, then you have square pyramidal. And when you have 4, you have square planar. And with that, I'm going to stop this complete description and stop it over here.